This is Music 320, Week 11, Lesson 3, where we're going to look at some spectral processing examples. Okay, so I'm basically looking at some of the examples that are contained in the Max MSP help help/examples FFT fun area. So you all have access to these. We're just going to look through them and see if we could understand what's going on in these particular examples. And again, if you're interested in building your own more complex spectral processing module, you can read through the other literature that's available on it. So I want to look first at Forbidden Planet. This is a fairly simple FFT spectral processing unit. Okay, so we've got a white noise generator here, and we've got basically a graphical display that we can use as an input into our spectral unit. So we have a PFFT tilde, and the name of that PFFT tilde, which I did build, is called FP_FFT. And the size of the FFT is 1024, and the number of overlaps is 2. So if we want to look into this FFT, the PFFT, we can double click on it, and this is what we find inside. So this is fairly simple FFT. And basically what happens is that we take the two outputs from the FFT in, the real and the imaginary numbers, and we multiply them by a value that comes from this index tilde. So I mentioned before that what comes out of the third outlet of an FFT tilde is a number that runs very quickly from 0 to the bin size. So in this case, from 0 to 1023, one less than the bin size. And we use this information to index into a buffer. And the buffer, which I'm going to pull out here, is basically filled by drawing in the graphics on the main page. So the graphics on the main page comes in here, goes through a list funnel, and the peak tilde puts it into this buffer. So it actually fills the buffer with the data. And then we access the information in the buffer and use it as a multiplier. So I'm just going to show you what that looks like. So if I draw in here, put the volume down while we're just looking at it. If I draw in there, then my buffer looks like that. Basically, the data that I've drawn in that graphic gets put into my buffer. And this is a buffer holds values between 0 and 123. In other words, the buffer has been sized specifically to hold 1024 points or values. So what happens then is that this index here is reading very, very quickly through this buffer and pulling the values out, which are between 0 at the bottom and 1 at the top. And those end up being multiplies for the data that's coming in. So this is basically the frequency bins in order, and we're multiplying the real and imaginary numbers that come out of the FFT. And so when we multiply, let's say bin 1 by this value, we get an output which has been scaled. And if we multiply it at the very end by 0, then that bin gets scaled down to 0. So we're actually able to kind of shape the successive bins, the amplitudes of the successive bins using this graphic. So let's close this up. I hope that's clear. It's fairly simple. Don't worry about exactly what the real and the imaginary numbers do. We need both of those values for each of the bins in order to do spectral processing. Okay, so I'm going to bring this up again. So there we just have low frequency sound. Okay, so you can see how this is working. We just have a bunch of presets there, but it would basically, we could put any sound source into this and use this as a kind of it's a spectral filter in a sense, where we're able to control the multiplications of each of the bins, each of the frequency regions by a value we put in here. So this will give us all the low frequencies. And this will give us all the high frequencies. Okay, so that's a very simple example. I'm just going to pull this open again so that you can see how it's working. Very often when we're doing spectral processing, we're multiplying the two values that come out of the FFT tilde in, and we're multiplying them by some kind of scaling factor. We're using this index tilde because as I said, the values that come out of here are going to be very quickly 0 through 124. And they match the data that comes out of here. So we'll get bin number 1, real and imaginary, and a value that says 0. And then we go and index into that buffer to get a multiplier. And then very quickly after that, we get bin number 1, bin number 2, the real, the imaginary, and a value that says this is bin number 2. We look into the index, we index into that buffer, and we pull out another value, and we use it as a multiplier. So it's a fairly simple spectral processing unit. Now, one of the things that we do often with spectral processing are forms of cross-synthesis, or what's sometimes called convolution. So I'm going to bring out the convolution workshop. Okay, in the convolution workshop, we have two sound sources. This is a rain stick sound file, and this is a drum loop. And we are taking these sounds and then we're mixing them. We're mixing a certain amount of, it's just a three-way mix really, a certain amount of the rain stick sound, a certain amount of the drum sound, and a certain amount of the convolved version of both of those. So let's just listen to it so you can hear how it works. That's the rain stick. That's the drum. And in the middle, we have a mixed version where in the spectral domain, aspects of both of those sounds are mixed together. Okay, and that's what's usually called cross synthesis or convolution. So I'm going to open up this PFFT tilde, which again, I didn't write, it's in your example, CW underscore FFT. And here they just have a 512 window, 512 sample window with 2 overlaps set up. Okay, I'm going to open this up, and so here, this is a little bit more complex, but it's technically not perfect convolution. But basically what's happening here is that the 2 values from sound number 1, the real and imaginary numbers that come out of the FFT tilde, FFT in tilde, are multiplied by the values from the FFT in tilde number 2. And pushing this through a car to pole tilde object. Now this is where the math starts getting complicated, but this is switching from Cartesian to polar coordinates. And the clip is just to make sure that we stay within a certain bounds. But when we do that, the information that we get out of that is a single value which represents the amplitude of the of each of the bins. So these are done in parallel. A sense, bin number 1 comes in from source 1 and source 2. So the values for bin number 1 in FFT1 come in here, and the values from FFT2 bin 1 come in here, are converted to amplitude values, and then multiply the bin number 1 values and then go to the FFT out. So I know this is complicated, but what's basically happening is if there is no amplitude in FFT1, then you're multiplying, in a sense, you're multiplying 0 by something and you get 0. And if there is amplitude in FFT1 and there's also amplitude in FFT2, then the multiplication is non-zero and you actually get some values. So what ends up happening is that the amplitude of sound 2 is imposed on the timbre or the spectrum of sound 1. And that's what you hear in the middle here. Okay, so that's what we call convolution. And there are some other examples in there. I know don't know if I want to bring this up or not because it's a bit scary looking. But there is, well, that's mine. I mean, this is the inside of a spectral delay unit that I built. And you can see that it's a little more complicated, but inside it, if you can read that, because it's kind of small, there's actually digital delays in there. And so this is a spectral unit that actually has a digital delay built in, so you can delay different bins a certain amount of time within the unit. The cross dog is another synthesis example. This is in the same folder, and this is an old school FFT. So I'm going to bring it up again. I don't want to scare people off too much, but this is an instance where rather than using PFFT tilde and the newer way of doing things, which is much simpler, this is an example where they have done everything the old way, which is to actually have an FFT tilde object and at the bottom an IFFT tilde object. And so they have end up with 4 of those. They're also using the car to pole tilde object to get the amplitude out of the FFT tilde. And then they're actually doing the multiplication, putting it through an IFFT. And then they've also built their own windowing system. So, you know, if you double click that, that's creating windows that look like this. And that's for shaping the overlapping bins and so on. So this is the way things used to have to be done. And you know, the theory of this is the same as if you used PFFT and just had the FFT tilde in 1 and the FFT tilde in 2. But you can look through that in more detail. There's also a phase vocoder example, which is more complicated. So we've sort of gone through in this tutorial a very simple to slightly more complicated to slightly more complicated. But please feel free to read through the articles by Richard Dudas and Cord Lip, which are really a step-by-step process of building a phase vocoder. It's not simple, but it's the results are quite amazing. So that's all I wanted to cover with spectral processing. As I mentioned at the very beginning, it's a complex topic. I hope you have a sense of how it works, and you can look at the examples and understand more or less what's going on in the inside. So, thank you.